Hi everyone, good morning. So today we will see a new topic, or maybe I can say the old topic only, which means already started the fitting in the last class, but we will see in little more detail. Okay, it is going to be a small class, just to understand the definitions of overfitting and underfitting. So let's just get started. So you might remember, by the way, like from the last lecture, let me just show you that we were talking about overfitting and underfitting, right? For example, let's suppose that you are fitting some, some polynomial, and that polynomial, if that is, having very high degree, then this polynomial is actually trying to capture everything, right? It is trying to capture everything. Do you remember this? Right? So, for example, I can say that even with the polynomial of the same degree, and if you see this particular polynomial, right? This particular polynomial is basically this one, right? So the one with the higher coefficient. So this is overfitting because it seems like it is trying to capture every data point. That's what we actually don't want. Okay, we don't want to capture every data point, right? So let's just understand this with one example, one real life example, I can say. Okay, so suppose there is a professor and these are the three students, right? So they are saying consider a math class consisting of three students and a professor. Okay, so he's a professor and there are, hello, yeah, I'm audible, right? Great. So if there is any issue, you can just let me know. So consider this professor, right? And there are three students, which are A, B, C. So he's a math professor. And now let's suppose that these students have different characteristics, which means let's suppose this student A, her hobby is just chatting, okay, just having the texting over the WhatsApp or any other platform, and she is not interested much in class, doesn't pay much attention to the professor. Let's suppose this is the characteristics of this particular student. Okay, let's talk about them one by one. So it is about the first student, which is this. The second student, let's say that his name is B, and his hobby is to be best in the class. Okay, he wants to be best in the class, mucks up everything that whatever professor says, too much attention to the classwork. Okay, he's putting too much attention to the classwork and he mucks up everything in the class, whatever professor says, right? And then there's a person, C, the third person, whose hobby is to learn new things, eager to learn concepts, pay attention to the class, and learn the idea behind solving the problem. So she is eager to learn concept, pay attention to the class. It is not like she's not paying attention to the class. She's paying attention to the class and learns the idea behind solving a problem. Okay. Now, we all know from our experience what happens in a classroom, right? We know that there are different kind of students. The professor first deliver lecture and teaches the student about the problem and how to solve them. At the end of the day, professor simply takes a quiz based on the whatever taught in the class. Okay, so it is like a very very much similar to whatever being taught in the class. So he take a quiz which is almost same as whatever was taught in the class. Okay, so suppose this is the class, this is the class work, and he is taking the test based on the class work. So let's suppose that these are the student performance I want to talk about, right? Based on a quiz that is based on the class based questions, basically, right? So let's suppose these are the three students which are just based on the class based questions. They are just answering the questions which are almost same as the class questions. So here this student whose hobby was chatting and all, so this student were able to correct 50% of the questions. The student who mucks up everything, right, since the questions were just based on the class, right, class, these are the class based questions, so that's why he is able to perform 98%. I mean, he is able to solve 98% questions. The person who was eager to learn and doesn't mug up everything, this person is basically able to solve 92% of the questions. Is this okay to everyone? Let me know that what is happening here. Okay, so who is the winner? Who is the winner, A, B, or C? As per this example, you can say that B is the winner, right? Because this person knows everything and he is able to solve 98% of the question. This is the quiz based on the class work, okay, at the end of the class. Now, here is a twist. Let's also look at what happens during the monthly test when students have to face new unknown questions, okay? So suppose that there's a monthly test when that student has to face new unknown questions which are not directly taught in the class by the teacher. Okay, let's just see. So this is the student performance on quiz on unseen questions, right? So he's a professor, and this person who was very simple, he this person was basically just guessing everything, either it is a class or it is a new questions. This person is able to solve 47% of the question. This person who claims to know everything, he was just able to solve 69% of the question. And the person who was eager to learn and actually learned the concept, that person was able to solve 89% of the question. Okay, so this is a performance on semester examination, or maybe you can say the unseen questions basically. Okay, the idea here is to have unseen questions. So in case of student A, did not change. It did not change, much. The and he or she whatever, he still randomly answer questions correctly almost 50% of the time, right? In case of student B, his score dropped significantly. Can you guess why? This is because he always memorized the problems that were taught in the class, but this monthly test contained the questions which has never seen before. Therefore, his performance went down significantly. Okay. In case of student C, the score remains more or less same. This is because she focused on learning the problem solving approach and therefore was able to apply the concept she learned to solve the unknown questions. Right. So she was focused on learning the problem solving approach. Okay, which means she was just understanding the concepts, not memorizing the things. Therefore, was able to apply the concept that she learned to solve unknown questions. Understood? Okay. I hope it is making little sense to you guys, right? So, this is class test or this is a semester test. So, in the semester test, as you can see, the C is the yeah. So, among all of these three, who is the winner? I think 89% is highest. So C is the winner here, right? Here it is the winner, but who cares? Do you really care about the class test? No, right? You only care about the final result, right? The semester test. So C is the final winner who has actually learned the things conceptually. Okay. So this is just a small example just to let you know that what does overfitting mean. So what you can say here, who is overfitting the model? Who is overfitting the model? B, right? B is basically just memorizing everything. So it was able to perform, as you can have the one-to-one mapping or the analogy that this class test means train set or test set. Here, this class test means train set, right? And this semester test means test data, right? So basically, as you can see here, that if you're memorizing everything, that means you are just overfitting. You are able to perform good on the train, but you will not be able to perform good on the test. Okay. So you can easily understand this. This situation where any model is performing too well on the training data, but performance drops significantly over the test data is called overfitting the model. Also, we have seen one more definition, I mean the clear definition of the overfitting yesterday itself, which is saying that it is a phenomenon where model is unnecessarily complex in the sense that portion of the model captures random noise in the observation rather than relationship between predictors and response. So overfitting causes the model to lose predictive power on a new data. Okay, so model is not able to generalize. That's called overfitting. For example, here, this is the overfitted model. This is the best fit model. It is underfit. Underfit means you're too simple, right? Too simple means you're underfitting. For example, itself, I think we had, some graph. Let me just show you. Yeah, okay. Maybe you can consider this particular example. Here, okay, let's suppose I want to fit a model. Then how does the underfit model will look like? Can anyone tell me? Tell me, is this the underfit model? Is this the underfit model? What do you think? Yes, right? Why? Because it's too simple. Okay. So it is underfit because it is too simple. Then what does this mean? Too simple means that it is not even able to perform good on the trained data. Okay. Okay. Too simple means it is not even able to perform good on the trained data. Right? Not good even for trained data. For example, if I just ask you this, sorry, if I just ask you this, tell me. I mean, intuitively, just tell me. Obviously, mathematically, there is nothing like this. You just intuitively tell me: is this underfit or normal fit or overfit? What do you think? As per this data, this is again underfit, right? Why? Because the normal fit could be little better, something like this. This is a normal. This could be some normal curve, right? This is some normal fit. So it is just still you can say underfit. Just intuitively, just tell me. Okay, I mean you can't tell mathematically or something. Okay, just intuitively, I'm saying that it is underfit, and the better could be this, right? This is better. This is seems to be best fit. What about this? Suppose, sorry, suppose if I say that you fit degree 50 polynomial, let's suppose this. What about this? This is overfit, right? Too closely remembering everything in the train, right? It's not good idea. Okay, so it's the overfit model. So overfitting basically model refers to the model that are trained data too well. Okay, I mean that performs on the trained data too well, performs trained data too well. Overfitting happens when a model learns the detail and the noise in the training data to extent that it negatively impacts the performance of the model on the new data. Okay, so model is learning too much the training data that it is even learning the noise that is negatively impacting the model's performance. Understood? Let me know. This means that noise or random fluctuation in the training data is picked up and learned as concept by the model. Okay, I mean it is concept means this is a previous analogy. Okay, the problem is that these concepts do not apply to new data and negatively impact the model ability to generalize. Understood the overfitting? Let me know. Okay. So underfitting is what? Underfitting refers to the model that can neither model the training data nor generalize the new data. Okay. So underfitting means that it is not even good for the training data. An underfit machine learning model is not a suitable model and will be obvious as it has poor performance of the training data. So by the way, which you think is easier to detect? Let's suppose you trained your model, which you think is easier to detect? That finally, based on the accuracy that you are getting, the train accuracy, test accuracy, which you think the easier to detect? Underfitting or overfitting? So generally, underfitting is easier to detect, right? Why? Because it is not even good on the train. Okay. If it is not even good on a train, you will get to know that, okay, there is some problem. Let me have some complex model. Okay. Not just very linear model or something like that. Right. Let me know if that is okay to everyone. Is this okay? So, which model is, can you hear me by the way? Okay, there might be some internet fluctuation. That's what, no, that's why I'm asking. Okay, so given that you have, some performance, then probably underfitting. Like, again, it is just intuitively or just the practically. I'm asking you that generally, I think, right? I mean, in gate DA they won't ask you this, that okay, whether underfitting is easier to detect or overfitting is easier to detect. I'm just saying that, okay, just in the practical scenario, underfitting is probably easier, right? Because it is not even good on the train data, so you will get to know the train accuracy itself is bad, right? So that's why probably it is underfitting. Okay. So underfitting is often not discussed because it is easier to detect given a good performance metric. Which means if you good performance metric, we will talk about these things later on. But we have seen one of the performance metric as, you can say, mean square error, right? This is also a good performance metric. Okay, it is a loss function also or performance metric also. So the remedy is to move on and try alternate machine learning algorithms, which means instead of linear, let's just try polynomial, right? Or maybe instead of polynomial, you try from degree 2 to degree 5 probably, right? Just use complex model. Just use little complex model. Okay, change your machine learning algorithm and use little complex model, right? Nevertheless, it does provide a good contrast to the problem of overfitting. So which means that underfitting is just a theoretical purpose thing. Practically, people doesn't face this as a problem. Are you getting my point? Why people doesn't face this as a problem? Because if you're not even able to do well on the train, you just use little complex model. That's very easy solution. People doesn't bother about underfitting. Are you getting my point? Do you think that people will bother too much about underfitting? No. Why? Because the moment you are getting less performance on the training, okay. I mean, you know that, okay, you are not able to do good on the training. What you do? What will you do? Probably you will be using the little complex model. So practically, people doesn't really care about the underfitting because it is easier to solve compared to the overfitting. Okay, compared to overfitting, underfitting is easier to solve. Do you all agree? Let me know. Okay, okay, great. So you agree, right? Because what to do for underfitting? Just use little complex model. So practically, people doesn't care about it. Okay, so it is nonetheless it is basically providing a good contrast, theoretically contrast to the overfitting. That okay, this was the overfitting, this is underfitting, but underfitting is something which is very easy to handle. So let's not really bother about it because the solution of this is that you just use the complex model. Okay, if you are not even able to perform well on the training set, then just use something else. Okay, you don't stick to your you don't stick to the easier models. Okay, we will anyway see the ways to remove the underfitting and overfitting also. We will see it in little more detail, but I'm just telling you one of the ways to use the complex model for the underfitting. Okay, and what is a good fit? Ideally, you want to select a model at the sweet spot between underfitting and overfitting, which means neither model is too easy nor model is too complex. You don't want to go for degree 50, you don't want to go for degree 1, right? So between degree 1, you can say between degree 1 to degree 50, there should be some best fit, right? Some sweet spot. So that's what they're saying, that you are interested in the sweet spot between underfitting and overfitting. This is a goal, but it is very difficult to do it in practice. Okay, I mean, what is the sweet spot? It is not easy to find. So it is very difficult. That's what they are saying. To understand this goal, we can look at the performance of machine learning algorithm over the time as it is learning the training data. So we will see that how to get that sweet spot. Okay. So we can plot both. Okay. So let's not worry about it. So you will get to know it in a few minutes. Okay, what it is written. So basically, let's just see this all the cases, which means let's suppose you are having a small training error, then probably you're overfitting. But if you're even having a small test error, are you really overfitting? Is this the case of overfitting in this particular region? Are you overfitting? If you're having a small training error, probably you're overfitting. But then you got to know you're also having a small test error. Are you really overfitting? Tell me. No, right? So we have seen this particular example in the last class also. So basically, we do have something like this, right? Here, if you are having a small training error, at the same time you are having the small test error, isn't it the sweet spot? But you are having the large test error. It means it is a overfitting, right? Suppose you are having, suppose you are having large training error and large test error. What does this mean? This means it is, yes, underfitting. If you are having large training error and a small test error, like there is no name for this. Actually, it is generally not possible. Do you think it will be possible? Only the magic can do this, right? Large training error and a small test error. I mean, see, theoretical it is possible. It might be possible. Your model is such that okay, your training and then you are getting your train data is this. Okay, your train data is this, but your test data is this. I mean, it could be very much possible. Very coincidentally, it is possible, and you also learn the model that is very nice on the train on the test, right? I mean, theoretically, I can say it is possible, but only the magic can do it, right? Only the magic can do it. Do we really want it? No, right? I want to train on the test train data. I don't want it, right? I mean, I don't. It is just a coincidence. Maybe maybe it is happening with this test data. Maybe the test data is changing. Then probably it is not a good model, right? Okay. So basically, it is just very rare case. Doesn't even happen. Neither we want it. Okay. Why we don't want it? Even though it is good on the test, because probably it is just a coincidence that we have this particular test data which is very ideal for this model. Maybe the different on the different test data it might do very very bad, right? So it is just something which is very rare. I mean, theoretically it is possible, but practically it is not possible. You can say something like this. Theoretically it is possible. Theoretically means mathematically you can say it is possible, but practically it is not possible, right? Okay. So possible but unlikely. Understood the four cases? Okay. So basically, what is happening here? Let's just see this graph. What they're saying, that let's suppose this is the complexity of the model. This is the error, right? So if you keep on increasing the complexity doesn't only mean that the degree of the polynomial. Complexity can mean something else also. I mean, degree of the polynomial can definitely be directly proportional to the complexity, in the sense that if you are having the complex models, then I mean, if you are having the higher degree polynomial, it is definitely the complex model. So for now, if you want, you can just replace this complexity by degree of polynomial. But this is not only the way to, I can say, to increase the complexity. Okay, there could be some complex model inherently. For example, For example, I can say, let's suppose neural network is one deep neural networks are one kind of model that we might see later on. Those are inherently complex than linear regression models. Okay, so anyway, complexity here you can understand that it is a degree of polynomial. But this is not the only way to increase the complexity. You can have complex models by itself. Okay, those are not even polynomial. Understood? So anyway, if you're increasing the complexity, then it is obvious that training error will decrease. Is this okay to everyone? Because the more complex the model, more flexible it is to capture the trained data, right? So if you're having a more and more and more complex model, it is like you're giving, more and more flexibility to learn more and more the training data. So obviously, the more complex model, it will always decrease the training error, right? It will never increase the training error if the model is more complex. As the complexity increase, you can even trim down the training error to almost zero to the extremely complex model. Okay, theoretically, I'm saying this, but does the very complex model are going to perform better on the test? No, right? The way you are increasing the complexity for some point in time, it is good. For example, degree 0 or y equal to some constant, it is not good, but y equal to x is little better. Y equal to x square, it is even better, but y equal to 50x power 50 minus 3x power 40 or something like this. Okay, these kind of models are not good, right? So basically, after some point in time, the test error will keep on increasing. Understood? So what is happening here? That you are increasing the complexity, you are getting better. Okay, you're getting better, but only till certain point in time. After that point in time, you will say that okay, you are increasing the test error. So this is the region where underfitting happens. This is the region where overfitting happens, and this is the region you can say. This is the region you can say is the ideal region or the sweet spot for us. Okay, this particular point is basically a sweet spot for us. Understood? Okay, so you can say. Okay, or maybe somewhere here. I mean, need not to be exact spot, but you can have somewhere here, which means the train error is not increased. It is only in the decreasing phase. Sorry, test error is in the decreasing phase, and train error anyway will decrease if you increase the complexity of the model. Is this understood? Okay. Now let's move to the little more definitions. So basically, underfitting is inability of the model to predict well on the levels data is that is trained on. So basically, it is not good for the training data itself. There could be several reasons for the underfitting. The most important is that model is either too simple or the features that you have, right? The features are not very good, which means there is no correlation between x and y. Okay, which means that x is saying that okay, what is weather today? X is basically saying that okay, maybe what is temperature, let's suppose temperature today. Y could be saying, let's suppose, um, you know anything. Maybe let's suppose that what do you think the Y could be? Any random feature could be that okay, I will watch TV or not. Okay, I mean, any very unrelated features. It could be very unrelated features. I mean, this correlation is not getting captured. Basically, you are thinking that X is good feature, but eventually it is not good feature. So it doesn't even matter that what you are doing, since there is no correlation. Probably you will not be able to capture the Y well. Okay. So anyway, like generally, the most probably the model is very simple. Okay, most probably the model is very simple. That is the reason that of the underfitting. The solution of the underfitting is to have the more complex models or engineer the better features. Okay. So generally, you will be basically having the more complex models because the features you anyway don't have. This is very hypothetical example. You don't have very irrelevant features, right? Generally, what is overfitting? Overfitting basically means, as we have seen, that it is doing very well on the training data, but poorly on the test data. Understood? So it is doing very well on the training, but poor on the test. Several reasons can lead to overfitting. One of the popular reason is that model is too complex, or maybe you are having too many features. Okay, if there are too many features, then also the model can overfit. Understood? Okay. We will see in more detail, don't worry. So basically, underfitting means model is very simple, overfitting means model is too complex, right? Let's just see this question, what they're saying. This is MSQ question. You train a regression model with a fixed model complexity, which gives very high accuracy. Okay, or maybe you can say very high accuracy means very very good model. Okay, on the training data, but much lower accuracy on the validation data. Okay, validation means like test data. You can just say that it is a test data. Okay, for now, if you don't understand validation, it's just same as the test data. Okay, you can say test data. Which of the following statement may be true? So select all the apply. This is an instance of overfitting. What do you think? Yes, right? Because it is, very good, very high accuracy on the training, but low accuracy on the test or the validation. So yes, instance of overfitting. Underfitting, no. The training and test examples are sampled from different distributions. So that could be also be the case, which means that let's suppose I am having house predictions, right? So if I'm having house predictions, I trained my model based on, let's suppose, uh, based on some city in Jaipur houses. Okay, this is my training set. House number one, house number two. This is my train, and I want to test it on the houses in, let's suppose, Watson. Okay, so some foreign country, right? Let's suppose I want to test. This is my test. Do you think it will do good? The distributions are different, right? Distributions are completely different. Okay, so it will not do good on this. So it will anyway perform bad on the test data. So distributions are completely different. So the train distribution and the test distributions are completely different. Understood? So hence it will not do good in the test, definitely. So also you whenever you collect the data, you need to make sure that both are coming from the same distribution. Okay, which means that, for example, when I was at Amazon, then suppose if I'm let's suppose predicting the sales. Okay, for example, some kind of electronics product, which means I'm predicting whether let's suppose tomorrow, or maybe let's suppose today is 20th. Okay, 20th of some month, let's suppose 20th of January. Then this is my training data, and if I want to predict, okay, let's suppose in future I have some data where I'm predicting that what will the sale on 25th of January. Okay, number of items. For example, if today is, let's suppose, 100 items got sold, then how many items are getting sold in 25th of January? In the train, let's suppose I'm saying 120. This is the train. Okay, train. Okay, sales on 20th. This is sales on 25th, right? Let's suppose this is the case. I'm having this train and this test. No, sorry, this X and this Y. Okay, suppose. Now, what is happening? Let's just assume that this is one kind of product. Okay, which means it could be, some electronics product. Okay, let's suppose it could be I'm training on some electronic product at Amazon. Okay, now someone says that, can I use your model? Can I use your model for my purpose? And my purpose is to have the predictions on, let's suppose, fashion product. Okay, I mean, may not be much correlation, which means that whatever model you are learning here, okay, whatever weights you are learning here, do you think it will do well on this fashion product also? May not be, right? Maybe the fashion styles are not that changing. Maybe, let's suppose, due to some, some launch of the mobile, let's suppose this particular, item is getting sale too much on this 25th. Maybe the shirt is not getting too much sale on the 25th January or something like this, right? So what I'm trying to say, that I mean, I don't know if you have understood it or not, but what I'm trying to say, that you have some different data set. Okay, numerically it looks same. Numerical in the sense that, okay, this is also sales, this is also sales. Here also in the train you have sales and all, right? Numerically it may look same, but it is coming from a different distribution. It is a different distribution. Okay, so in that case, your whatever you do, you will not be able to do well on the test, right? Because you're testing on something else. So how you can do? You're not even supposed to test on this, right? If you're doing it, then how you can do well, right? So that is why this could be the overfitting. And it could be the case that if you're doing too much good on the training and not good on the validation, it could be the case that you have sampled from two different distributions. So three is also the answer. Is this understood to everyone? Let me know. Okay, need not to be just overfitting. It could be the case that you're training on completely different distribution. Okay, let's just do this question. A regressor with fixed model complexity trained on smaller data is less likely to overfit compared to one trained on the large data set. Just try this question. Just tell me. Just think about it too much. Give it a good thought and let me know what is the answer. Okay. So what did you answer? True or false? So what they are saying is that you're don't worry about the increasing or decreasing the model complexity. You're training on the, I mean, you're just changing the size of the data set, right? You're training on the smaller data set that will overfit, or on the large data set it will overfit. Small On the small data set, is it less likely to overfit or more likely to overfit? See, what is overfitting? Overfitting means you're learning, right? You're learning the train too much. So if it is less data, it is easier to learn or hard to learn? See, if you're saying this is true, then what you're actually saying that increasing the data is actually bad, right? Because if you're increasing the data, you may overfit. Do you think it will be bad? Do you think it will be bad? If you're increasing the data, then will you think it will be bad? You will be overfitting? It should not be the case, right? So that's what is false actually. Because what they're saying, that if you're the smaller data set is less likely to overfit compared to the one on the larger data set. No, larger data set won't overfit. Because if you're having large data set, then it is very difficult to basically remember the data. Okay, assuming that you are not changing the model complexity. So so basically what they are saying, that it is false, because a specific regression with a fixed model complexity is more likely to overfit to the noise to the training data when trained on the smaller data set, right? Therefore it is more likely to overfit. So which means if you are having a smaller data set, just few examples, right? You may overfit. Is this okay to everyone? Okay. Large data set, difficult to overfit. Difficult to overfit. Let me know, that is fine. Yeah. So how does it depend on the size of the data set? It basically depend, right? Because if it is a smaller data set, let's suppose only three examples. Don't you think it is very easy to remember all these three examples even with the lower polynomial degree? Let's suppose you are having just lower polynomial degree. Don't you think it is easier to remember all these three examples? But if you're having large data set, then it is not easy to overfit, right? It's very, very difficult to overfit here with the simpler model at least, right? Degree 100 polynomial can definitely overfit, but with the simpler model, it is easier, it is difficult to overfit. Okay. So you can say that in other words, it's very good discovery that if you want to remove overfit, remove overfit, then what is the first way? Use less complex model. That's what we have seen. What could be the second way based on the data? Use more data or less data? What do you think if you want to remove overfit? Use more data, right? Use more trained data. Okay. You can say in this words also. That's also very good understanding. Okay. This is very, very good and very, very important question. Just let me know what is the answer here. Let's suppose there is no noise, then there is no overfitting. What do you think? This is true or false? If you are saying this is false, then what is the reason? What is the reason behind it? Do you want to speak? You can just speak and let me know why you are saying this is false. Randomly picking model fit well just on the data. No, if there is no noise, you just let me know. Fluctuation. No, true because overfitting means learning the noise as well. If there is no noise, there is no overfitting. Okay. True as no complex patterns because on training model is more complex. Okay, no. None of the answers are satisfactory because probably this is a little tricky question. See, if there's a noise, okay, let's just consider that there's a noise in the data. If there's a noise, then definitely, let's suppose the data is not very perfect. Okay, if there's a noise, then definitely, if you try to learn everything, there might be overfitting, right? If there's a noise, there could be definitely overfitting. Okay, so Tejas is saying false. It will less overfit because, but not overfitting. No. Okay. So suppose there is a noise, then obviously it will be overfitting, right? If you do it, I mean, if you use the complex model. But let's suppose there is no noise, can it still overfit? If you use, let's suppose, not, no, I mean, if you use like similarly complex model, if the data is, let's suppose, having no noise, what does no noise scenario mean? Let's suppose data is coming from a very ideal function. Okay, whatever is the function, it is well-defined function, which means let's suppose the data is coming from the sinusoidal curve. Okay, let's suppose this is the data. Suppose this is the data. Uh, this is a data distribution which is coming from the very ideal function. Now, if you train on this data, and I'm assuming there is no noise, which means the data is it is same. Okay, just a second. So suppose that data is very ideal. In that case, do you think you will be overfitting? You can still overfit, right? Why that is the case? Even though data is ideal, right? But suppose that you have this, I mean, this is your complete data, but in the train you have this. Okay, so what I'm trying to say, that this is your complete data, but in the train you have just this. Or maybe something like this. Okay, I mean, in between you don't have. Okay. So basically, you may still overfit, right? You don't know that where to go, and then in between you can do anything, right? In between you can do anything. You may still go like this, right? Just trying to remember everything. You may still go like this, something like this, right? And then the test data came to you. The test data is saying, let's suppose the test data came to you. Let me just picture it here. Let's suppose the test data is came to you. So whatever is seen as a white dots is your test data. Is it performing very good on the test data? Tell me. The situation could be very worse, right? In the sense that currently I'm just having this kind of model, but the situation could be very worse. So for example, you can have this kind of models. Okay, suppose you have this kind of model. Now you have your test data. Okay, so suppose whatever is seen as a white dots is your test data. Is this doing very good on the test data? Tell me. No, right? It is not doing very good on the test data. So basically, even though your data doesn't have noise, right? But if you are using the complex model, it may so happen that you are unnecessarily twisting it too much, right? So which means you are not able to generalize. Okay. In the test, if you are having this kind of data as a test data, you're not able to generalize. Are you getting my point? You can still overfit if there is no noise. Let me know. Okay. Because you're just seeing the train data. Okay. Because you're just seeing the train data. Understood? Since you're just seeing the train data, that's why you can still overfit. So that's what it is written here. Okay, you can just read out this question I've taken from Stack Exchange. Okay, you can read out these paragraphs here. So they are saying yes, it is possible without noise even. Your XY pairs completely satisfy this, which means you are completely satisfying the ideal function. Oh, okay, so sorry, actually I think there's some internet issue today. So what they're saying that you take some training data and then your test data could be in between. I mean, you're taking the every second point as a test, which means you're taking this is a train, but now this is a test, this is a test, this is a test. So basically, since you're only fitting on the train, you don't know the test, right? So it is still possible to overfit something like this. Okay, you can have very bad model which is just paying too much attention on the train. It doesn't twist itself based on the test. It is not generalizing well. Understood? Okay. So it was a very good question. Now just let me know what is the answer of this. Which of the following statement is true? If there is no noise, then there is no overfitting. Is this true? This is false. That's what we have just seen. Right? This is false. Overfitting may improve the generalization ability of a model. Generalization ability means it is able to do good on the test also. Obviously, no, right? Obviously, no. Generalization error is monotone, which means it doesn't change with respect to the complexity of the model. Generalization error basically means test error. No, right? If you are having very simple, the test error will be high, and very complex, then probably the test error will also drop. Okay. So this is no. More training data may help prevent overfitting. Yes, that's what we have already seen. Yes. So this is yes. Why? Because if you are having more data, then basically you are getting the exposure to the better pattern. So obviously you will not be able to memorizing. You will be able to learning more. Okay. If you are having more data, you will be able to learning more. Right. Yes, that's the answer. Increasing trend data size would help better approximate the true distribution. Right. Okay, whatever is the true probability distribution from wherever I'm drawing this data, okay, that nobody knows. We just want to, approximate that distribution. So if you are having more training data, you will be having the better approximations. Okay. So suppose we predict the target variable by using eight models with different degree polynomial features. So they are saying you are having eight models, one, two, three, four, five, six, seven, eight. Okay. So you are having eight models here. Now what they're saying, which of the following plots display training and validation error of these models? Okay. So which plot is saying training? If we are, let's suppose, this is the mean square error. So if we are, let's suppose, having these degrees, okay, let's suppose this is 0 degree polynomial, this is 2 degree, this is 4 degree, 6 degree, like this, okay, right? So now tell me which of the following plot is telling you that this is train, this is test. So maybe I can, sorry, yeah. So can you tell me, if you are increasing the complexity of the model, this is the complexity degree, right? Then you should be basically, for the train you should be decreasing, okay. So for the train, what is the answer? I think C is the answer. For the test or the validation and test actually same. What is the answer? Will it be always increasing? No, right? We have seen this. That this is a sweet spot, right? It will decrease first, but after some point in time, if you having more complex model, it will start overfitting. So you can say this is overfitting region. Okay. So that's why B is the answer. Okay. This region is overfitting region when the test error is started increasing. This is basically the underfitting region. Okay. Where neither the train nor the test, both are performing bad basically. Okay, so this is B, this is C. Now let's just see this question. Okay, let me just read out this question for you. So what they are saying, suppose these are the four plots that they have given. Now they are saying that if x-axis is number of training examples and y-axis is the test error, then which of the following plot is the best? Which means, can I put x here, number of training examples? If number of training examples are increasing, the test error will decrease. Number of training examples is increasing, the test error will be increasing. Number of training examples and the test error, what is the relationship? Number of training examples, if you keep on increasing them, then you will be able to generalize more, right? So I think since you are able to generalize more, then test error will decrease only. It cannot increase, right? It cannot be, I mean, it could be little bit fluctuation, that's fine, but it cannot be keep on increasing, right? You keep on increasing the number of training examples, the test error keep on increasing. No, I don't think, right? So A should be the answer. Number of training examples, X is number of training examples again, and Y will be the training error. So what is the answer here? See, the if you increase the training examples, okay, if you increase the training examples, then the training error, suppose the model is fixed, okay, you are not changing the model. If you increase the training examples, we have seen this, right? Training error will always increase. Okay. So training error will increase only. So it means it is B, because now you are having more terms like this, right? Y minus y cap whole square, y minus y cap whole square, right? Like this. Okay. I mean, you are having more terms to deal with. So obviously, training error will also increase. We have seen this in the previous classes. Do you remember this? In one of the class, I told you this particular statement. Anyone remember? Okay, great. So now tell me, if you're increasing the polynomial features, which means you're introducing x cube, x power 4 like this, right? Then test error. So what do you think about the test error? It will decrease initially, and then if you're having more complex model, it will start increasing, right? So I think C. Okay. So order of polynomial feature, if you keep on increasing, if you're adding order of polynomial features, cross validation. Okay, this cross validation test actually same. Okay, don't worry about this. The cross validation term. So actually, it is also C. I mean, these are actually same. Okay, don't worry about this cross validation. We will talk about it later on. Okay. For now, you say that it is same. It is actually almost same. Okay. So what is the answer? Answer is A, B, C, and C. Right. So answer is A, B, C, and C. I mean, probably they have, yeah, same as the test error, right? They have also written the same thing. The cross validation and test error is same. Okay. D could be some random graph. Okay. I don't know. Um, First it is increasing, then decreasing. Could be some random. Okay. Just a random example. Just a random graph. Okay. Just tell me which one is train error and which one is test error. If you increase the number of random examples, the train error and test error, what will you say? Keeping the model complexity fixed. Everything else is fixed. Suppose this is one, this is two. Train error is which one? One or two? So train error is actually will keep on increasing, right? Train error should be increasing. Number of training examples if you increase, right? So train error should be two, test error should be one because you will be able to generalize more. Okay. If you keep on adding the examples, you will be able to generalize more. So that's why the test error will be decreasing. Okay. Okay. Which one is your train error? Let's suppose this is one. Let's suppose this is one. Just a second. Yeah, this is one. This is two. Number of parameters means number of weights. I mean W0, W1, W2, W3, like this. Okay. Number of parameters is this. Okay. So basically, number of parameters, or you can say it is same as the complexity of the model. More parameters means model must be more complex. Okay. So if we increase the complexity of the model, the training error should decrease, but after some point in time, the test error will increase, right? So this is two, this is one. Is this understood? Okay, great. Yeah, so this is the slide that I just made a question out of these two, this slide. Okay. How the parameters is complexity? Because parameters means you are having, for example, you are having the complex model. For example, you are introducing the features x cube, x power 4, x power 5, x power 6. For every of this feature, you will be needing one parameter, right? Let's suppose w1 here, w2 here, w3 here. So if you are having more parameters, right, it means you are increasing the complexity, right? If you're having less parameters, probably you are just having w0 plus w1x. Maybe your model is very less complex, right? If you're having more parameters, more weights, more parameters always means that it is very, very complex model. It need not to be polynomial model. Okay. For example, in deep learning, like deep learning is not very much in the syllabus. It's just introduction to the deep learning that is there in the syllabus. But in deep learning models are actually very complex models. Okay. Why? Because they have many, many parameters to learn. There are many, many parameters that you need to learn in the deep learning models. Okay. So that's why these models are very complex models because the parameters have the ability to capture the things, right? You're providing the more parameters, which means you're learning more. Okay. You're learning more. Yes. So ChatGPT must be having, millions and billions of the parameters. It's very, very complex model. Okay. So is this understood to everyone? This slide? I mean, I just made a question out of this slide, but I hope you understood this. Now let's solve this question. What they're saying. This is about the generalization and overfitting. For each of the following statement, which combination of italicized words correctly completes a statement? So, for example, should I choose low or high here, and should I choose low or high here? Let's just see. That's an interesting question, right? If the model has model has lower high training set error and a lower high test set error, then model generalize. So, what should I pick here? For low, you can just write L. For high, you can just write H. Okay. If you don't want to type fully, then you can write LL or LH or HL or whatever. Okay. So if you are generalizing well, then you can say that low training and low test, right? Okay. If the model has lower high training set error and lower high test set error, model overfit. So what should I pick here? High training set error, sorry, low training set error and high test error, right? Then model will overfit. Okay, great. What about this? If a model has the model underfit, underfit means I think both high, right? Okay. We can fix underfitting by either choosing more or less complex model, or adding or removing the feature. So how to fix underfitting? More complex model, right? I need to go for more complex model. And what are the features? By adding features, right? Because I want features means the parameters, right? I mean, if you're adding the features, the parameters will get out, add-on model will get more complex. I just want to increase the complexity of the model, right? I probably want to add more features because the previous features might not be relevant enough to capture the things, right? Capture the pattern. So maybe I need to that's why it is performing bad on the even the train. So that's why I need to add probably more features. Understood? Because the previous features might not be good enough to even capture the train. We can fix overfitting by either using more or less complex model, or adding or removing features. You want to fix overfitting, right? So I think less complex model and removing the features, right? Okay. Is this understood to everyone? Okay. So probably now you know that that for the underfitting or overfitting, what to do, right? For the overfitting, what we can do, by the way, to remove overfitting, less complex model, maybe more training data, right? And what about the features? Maybe, I mean, basically I don't want to remove the relevant features anyway. Probably I can just remove the features which are very less having the correlation. Okay. Okay. Remove irrelevant features, I can say. Good features I never want to remove. Okay. Probably I can remove the irrelevant features. It is trying to even learn everything from even from these irrelevant features. Okay. Irrelevant means not having much correlation with y. Okay, something like this. So it is trying to learn minute details from those features also. So I can just remove them. Understood? Okay. What about underfitting? How to remove underfitting? Just opposite of this, right? More complex model. Should I have the less data? Should I have the less data? Should I say that have less data? See, having less data probably can remove underfitting or okay. So if you are having less data, then I mean, actually, this is never a good idea to have the less data. Okay, even it is somehow just helping you, but you don't want to help yourself by, you can say by getting broken, right? You don't want to have the less data anyway. Okay, even if it is helping you just to showcase. On the okay, I don't have it, but you ideally don't want to have less data. So probably you add more features, right? Hello, hello, is my voice broken? Is this better now? So what I just said, that you probably don't want to, you probably never want to have the less training data. Okay, even if it is helping you somehow, you don't want to do it. Okay, less training data is never a good option. Okay, why you want to have less training data? Okay, so probably just have more complex model, add more features like this, make it more complex. It is very simple thing. Okay. So this is the conclusion about overfitting and underfitting. This is the introduction to overfitting and underfitting. We will see one official term. I mean, there is a in the official syllabus there is a term called bias and variance trade-off. Okay, we will see this later on. Bias variance trade-off. There also we will talk about underfitting and overfitting. Okay, bias variance trade-off. That's exactly I think the same term mentioned in the official syllabus also, and it's also very important thing to understand. Right? We will see this later on. First, we will see something called as regularization. which actually helps to have the lesser complex model. Okay, so regularization achieve this. So we will see that how to remove overfitting using the regularization as the next lecture. Understood? So regularization is our next topic. Okay, cool. Thank you, everyone. Thank you so much. Let's just meet in the next lecture for the regularization. Thank you.